So I'm happy to present my work on fatigue lifetime prediction of additive manufactured alloy. So this work is collaborated from some of my colleagues and friends here. Some are here, some are not here. So in the first part, I will start from the introduction. So as we know, that additive manufacturing is quite popular. There's a lot of advantages, such as it's a kind of digital manufacturing. You can manufacture the components and parts very fast, efficiently, and they can increase the efficiency. And now it is widely used in some industry. And there are also some disadvantages, such as the microstructure, which is induced from additive manufacturing, demonstrate anisotropic heterogeneity, such as there are some holes, some cracks in the material, and also some residual stress. And this limits the application of this material, especially in fatigue application, because in the fatigue lifetime prediction, the damage will be increased, and especially high cycle, very high cycle fatigue, then this may lead to crack initiation. So the question raised, what are the crack initiation mechanism and the lifetime prediction methods? And of course, there are already some work on this topic, such as a lot of work focused on defect on the study the effect or defect on the lifetime, and also try to propose different kind of methods to account for the crack initiation mechanism, such as the competition mechanism of crack pores effect or the microstructures. And in addition, there are also some methods which are proposed to predict lifetime of this additive manufacturing materials. It should be noted because of the anisotropic and the heterogeneity of the material in the material. Here we can see that the S1 curve here demonstrates a big scatter. That means even we test the material, the same condition, the fatigue lifetime shows a big uncertainty. So this is a big problem for the engineering application. So we try to understand this mechanism. Also, we try to propose some methods to account for this complicated phenomenon. So in this analysis, here we focus on two parts. One part is we try to analyze the crack initiation mechanism and also some factors. And also we try to study the lifetime prediction for this material, especially focused on short crack growth part, because this is very important for very high cycle fatigue. Take into account maybe 80% or even 90% of the total fatigue lifetime. So here, of course, here this material here we use is a kind of popular aluminum silicon mechanism material, and here there are some parameters for the manufacturing process, and here the input energy density for this material here, and for very high cycle fatigue test, we use ultrasonic fatigue test because there's a high frequency, and of course the frequency effect should also be studied, and the stress ratio here we also analyzed. And here we can see that from these two figures, this can demonstrate clearly that the multi-pore boundary structure, which is a kind of anisotropic characteristic of this material, and also there are different kind of crack defects here in this material, either in the border between multi-pore boundary or inside the material. And from this CT analysis, we can see that there are also different kind of shapes of cracks, and most of the cracks are irregular. And of course, this will have an effect on the fatigue life or effect. And of course, here in the material, we can also see that the material here, we can see they can be divided into fine zone, heat affected zone, and coarse zone. And also there are some tactic silicon precipitation here shows in this figure, and this may also have an effect on the fatigue lifetime, on the fatigue effect. And from different orientation, either from horizontal build material or from the vertical build material, here you can see that the microstructure, they are quite different. Some columnar grains and together with equal axis grains, and there are some quantification of this microstructure here. And from practice surface observation, and see most of the cracks, they are start from either from the pores or lack of fusions or the material, which are because of this additive manufacturing process itself. So this is a very especially very pronounced in this material, in this aluminum silicon mechanism alloy here. And in addition, very high cycle fatigue, of course, we also found this crack initiation from inside, which shows demonstrated a fish eye. And from here, fish eye, we can see that from along crack length, we can see some grains, they are refined, and some nanograin we found around the crack length, and we can see they are non-uniform. Some parts they are nanograin, some parts they are not, and also along the crack length, also the microstructure, they are quite non-uniform. This is because of the formation of the nanograin is because of the pressing. This is the pressing stress, which is due to shear stress at the local location of this crack surface. And of course, in the horizontal vertical to the fatigue surface, we also will cut, and we've tried to do an analysis or EBSD analysis. We found a lot of multiple cracks we found along this section, and this is a crack initiation site. That means there are a lot of small cracks initiated, and then they coalescence, and later on they form the main crack, and which lead to the final failure. So this is the total failure size in very high cycle fatigue. And of course, we also analyzed the short crack growth study. We try to quantify it, and then we found we try to stop cracking growth at a different size, different cycles, and we found some phenomena. And also we found multiple crack initiations, multiple crack starts at different locations, different stress concentrations, and they start and coalescence to the final failure. And here they are the quantification of crack growth versus stress intensity factor change. And here the phenomenon is that one important phenomenon is that here we can see some fluctuations here. Sometimes stress this dA versus dN increases with delta K, sometimes decreases. This is the short crack phenomenon, because when the crack propagate along reach the grain boundary, it will stop and rest a little bit, and then when it overcome this grain boundary, it will increase with this delta K. And so in order to start this crack growth phenomenon, especially in very high cycle fatigue, so this is, I think the phenomenon is quite complicated. Here, one method we use is machine learning. Machine learning, the advantage of machine learning is that we can include a lot of factors together, such as stress intensity factor, stress ratio, temperature, and also the maximum stress. And with all this material as input factors, and here the machine learning method we use the ensemble learning. So this is somehow is different from this artificial neural networking methods, and it has some advantages of assemble all the learning methods together. But the disadvantage is that it takes a lot of time. And here we another challenge for this method is that we need a lot of data for the fatigue time prediction. The experimental data is very limited. So here we use a fourth order polynomial to expand to enlarge the databases and to enlarge to 1,000 and something data points, and then we try to use it for the prediction. And of course, some parts of the data are used to train this method, and some parts are used to predict. And finally, we found that our prediction is quite in good agreement with this analysis. And also from the sensitivity analysis, we found also the delta K has the most important effect on crack growth effect, followed by T temperature ratio and the maximum stress. This is the machine learning. And the second part, I will just go through very fast with the, because this part is mainly on crack growth analysis. We also need to know the total fatigue lifetime. Here, we also use the crystal plasticity analysis. For this crystal plasticity analysis, here we fit some parameters here, such as elastic, both elastic and elastic plastic parameters here for the cyclical analysis. And we assume that inside the material, there are different kind of pores, different kind of inclusions, and the size, their variation, and we can see that there are some stress concentrations around the pores and around the inclusions. And here, and for this analysis, we can see the cumulative plastic strain, which also as a function of cycles, there are increases. And when they reach some cycles, they not increase so much, more or less they are saturated. And this gives us some insight, some hints that we can use plastic strain as a fatigue indicate parameter. Here, this is a key point. Because we need the fatigue indicate parameter to calculate, to correlate the plastic damage with fatigue lifetime. And here we use 3 different FIP fatigue indicator parameters. Here, one is the when it's saturated and the accumulated plastic, and also this is the accumulated plastic damage over a grain size. And the third one is a kind of SWT model, which we take the elastic part. We assume that in the later on, the damage is not so big. And here we can see that the model 2 performs very best, because here in our analysis, because the damage is very local, it's located only in the pores or in the non-metallic inclusions. So this model here, number 2, performs best. And of course, for the different kind of specimen which manufactured either horizontal or vertical, and with this method can also be calculated. And here you can see that the fatigue strength of this vertical specimen is lower than that manufactured horizontal. This is because of different kind of this microstructure, and also the different kind of orientation of the cracks. And the stress ratio can also be predicted by using this method. And we can see that with the increasing of stress ratio, fatigue strength decreases. And of course, the defect size also will have a effect on fatigue lifetime. And here we see that the fatigue lifetime decreases as defect size increases. And of course, the orientation has an effect on the lifetime prediction. So with that, I will conclude my talk here. And there are 3 conclusions, and I'm happy to take questions. Thank you.